So I thought of this slight twist on the homework question involving a tennis ball and a basketball. And I thought I'd go through it and maybe it'll help lead you to doing that particular homework problem a little bit easier. So we have a tennis ball and a basketball stacked on top of each other, same setup. I gave particular masses. I looked these up online, and I chose an initial height of 1.5 meters. So the first step is to find the speed at the bottom of the fall. And for that, we're just going to use mgh is equal to 1/2 mv squared. At the top of the drop, the kinetic energy is 0, so it doesn't appear on the left-hand side of the equation. And we'll set the height, the y equals 0 at the bottom of the drop, so it doesn't appear on the right side of the equation. And then we can cancel the m's and only do the calculation once, even though there's two objects of different masses. And we can find this v. So it would be 2gh is v, that would be v squared, so we'll take the square root of it. So where's my little scratch spreadsheet? So h is 1.5 and v of drop is square root of 2 times g, which is 9.8 times h, and that gives me a 5.42 meter per second result. So that's the easy part, and I hope that you could all do that fairly easily. There will probably be a question on the final exam very similar to that. And two, the second thing we have to do is we have to let the basketball bounce elastically off the ground. Now this is actually a lot easier than a typical elastic collision. And the reason it's easier is because the ground isn't going to be affected by the basketball bounce. Earth is not going to be displaced at all by the basketball bounce. So all we have to do is reverse the direction of the basketball's velocity. So at this point, we have a basketball which is moving upward with 5.42 meters per second. And then we have a tennis ball. Tennis balls are green, right? Which is moving downward at 5.42 meters per second of speed. So now we have to handle the elastic collision between the basketball and the tennis ball. Now the video lesson that I posted talks about a method of doing this calculation that involves the center of mass coordinate system and the velocities relative to the center of mass. So I'm going to do that real quick here. First, we find the total momentum, which is m1v1 plus m2v2. So let's call m1 the basketball. So that's 0.625 kilograms. and V1 is 5.42 meters per second, plus the tennis ball mass of 58.5 grams, so that's 0.0585. So the decimal point moved 1, 2, 3 places to turn grams into kilograms. And its velocity is minus 5.42 meters per second. So we have some upward momentum from the giant basketball and some downward momentum from the little tennis ball. And I have to put in my M1 is 0.625, M2 is 0.0585, and V1 initial is equal to the velocity plus 5.4221766685, and V2 initial is equal to minus of that initial velocity. So P total initial is M1 times V1 plus M2 times V2. And I'll just write it down with 3 significant figures, but I have all the significant figures in my calculator. 3.07 kilogram meters per second. So in my elastic collision method, my second step is to find the center of mass from the idea that the total momentum is equal to the total mass times V center of mass. It's a calculation that looks like a regular momentum calculation. It's a mass times velocity, but it's for more than one object. So the mass we use is the total mass, and the velocity that we get out of it is actually the center of mass velocity. So we set 3.07 is equal to total mass is 0.625 plus 0.0585 times V center of mass. So then we just have to divide to find V center of mass, and so it's equal to that momentum divided by parentheses mass 1 plus mass 2, 4.49 meters per second. So notice that the center of mass velocity is not that far from the velocity of the basketball itself. It's upward, it came out positive, and it's only 1 meter per second slower. And that's because the basketball is a lot more massive than the tennis ball. So now, I only care about the basketball. So now I'm going to find the basketball's velocity relative to the center of mass. So this is V prime is equal to V minus V center of mass. So this V prime is the velocity relative to the center of mass. So we just take the basketball's actual velocity, 5.42, minus the center of mass velocity, 4.49, is equal to, so this would be V1 initial prime is equal to the regular V1 initial minus the center of mass velocity, 0.928. per second. And notice that even though if you type these values in as written, you would not get a third decimal place. I do have a third decimal place because I kept all the accuracy in my calculator. So now we just reverse v prime. So the new v prime is equal to minus 0.928 meters per second. That's it. So now, finally, we can convert back to regular velocity. If v prime is v minus v center of mass, then we can take v prime plus v center of mass to find the regular v, which is minus 0.928 because we reversed it, plus the center of mass velocity was 4.49 is equal to v1 final prime is minus that, and v1 final is that plus the center of mass equal to that plus the center of mass is 3.57 meters per second. Now, when you do this for the homework question, you'll have to use the tennis ball in here and find the v prime for the tennis ball using the v of the tennis ball, which is actually just negative of this. So now we can go back to our overall multi-step process is we can figure out how high the basketball can go with that initial velocity, 1/2 mv squared. This is now at the bottom. The basketball is going upwards after kicking the tennis ball up really high. And that basketball's energy turns into mgh. It turns into height energy. And what do you know? We can still cancel the masses. And we're solving for h now. So we get v squared over 2g is h. So this is 3.57 squared over 2 times 9.8. So h1 final is that squared over 2 times 9.8 in parentheses for the bottom of the fraction, 0.65. Oh, yeah. So even though the basketball was initially dropped from a height of 1.5 meters, and all the collisions are elastic, so we still have all of our energy, the basketball in the end only attains a height of 0.65 meters. So that is how to handle an elastic collision in this vertical situation where we have to go back and forth between velocity and height in a regular conservation of energy calculation, and we also have to do this elastic collision to deal with the middle of it.